Hi everyone, this is Amine Chellali from Université Paris-Saclay. I'm going to present our work entitled The Impact of Visual and Haptic Feedback on Keyboard Taping in Immersive Virtual Environments. This work was co-authored with Herfort, Guillaume, Loup, and Marie-helene Ferrer. Taping on a keyboard is an important task when simulating workplaces in immersive environments. It can be useful when writing an email or updating a patient's file in the OR. In the real world, achieving a good typing performance requires using multiple fingers and relying on haptic cues while feeling the opposite forces when pressing the keys. However, some limitations of current VR technologies, such as the lack of haptic feedback and hand tracking accuracy, decreases typing performance in VR. Some solutions have been explored to improve typing performance in VR. Physical keyboards co-located with their 3D counterparts provide realistic haptic feedback and are usually associated with high performance. However, they require precise tracking and bulky equipment. They are difficult to implement when users are expected to move inside the virtual environment. On the other hand, mid-air virtual keyboards are easier to implement and reposition but lack haptic feedback, leading to lower performance. Other approaches include visual cues to compensate for the lack of haptic feedback, active devices, and passive probes. However, no gold standard exists, and some methods are yet to be evaluated. Moreover, other design elements are to be considered. While expert tapists typically use all 10 fingers for better performance, some studies suggest that using just the 2 index fingers in VR can be more effective. In addition, expert tapists spend less time looking at the keyboard, so design elements that force the user to look at the keyboard more than usual could negatively affect their taping experience. Therefore, the objective of our study is to investigate how visual and haptic feedback influence taping performance and user experience in VR. Here we will focus only on using native hand tracking systems, and we will use only the index fingers for taping. We have defined the following general hypothesis for our study. First, we expect that combining the physical keyboard with visual cues will enhance taping performance, reduce mental workload, and improve usability. In addition, the physical keyboards, by providing spatial landmarks, are expected to reduce the need to look at the virtual keyboard, while visual cues will increase it. For this experiment, the participants used a head-mounted display with hand and gaze tracking to perform a text copy task using the 2 index fingers. The stimulus consisted of 6 sentences composed of letters from A to Z from the French phrase set of Franco, Salvador, and Leva. They were not allowed to correct their taping errors. The study followed a mixed design with 2 within subject factors related to visual feedback mechanisms with 2 conditions each, and 1 between subject factor related to the haptic feedback mechanism with 3 conditions. We recruited a total of 24 participants that were divided into 3 groups according to the between subject factor. Each participant tested then the 4 visual feedback conditions in a counterbalanced order. The hover visual feedback consisted of changing the key color when approaching the virtual key, while the keypress feedback consisted of changing the color when the finger was in contact with the virtual key. In the desktop condition, the physical keyboard was superposed on its 3D model. In the surface condition, we have used a 3D print of the same keyboard, but with no keys. Finally, in the mid-air condition, there was no physical contact. We collected both objective and subjective measurements. Objective measurements consisted of performance data and eye-gaze behavior, while subjective measurements included the nasal-TRX to measure the mental workload and the usability questionnaire. The results for the interview rate show a significant interaction between hover and key press, with participants performing better when only the key press was activated. The performance decreased significantly when both mechanisms were activated at the same time. No other significant results were observed. Regarding the error rate, the results show a significant main effect of hover feedback with participants performing better when it was activated. In addition, the results show a significant main effect of the keyboard, with participants performing better in the mid-air condition than in the desktop condition. Regarding the time the first key press, the results show a significant main effect of hover, with participants pressing the first key faster when hover was deactivated. For the gaze behavior, the results show main effect of key press, with participants spending more time looking at the keyboard when it was activated. We find also a significant main effect of the keyboard, with participants spending less time looking at the keyboard in the desktop condition. The results show also a significant main effect of the key press visual feedback on the nasal scores, with a decrease in the mental workload when it was activated. Finally, the results show a main effect of the keyboard on usability, with lower scores in the desktop condition as compared to mid-air condition. No other significant results were observed. To summarize, keypress visual feedback improved the typing speed and reduced the mental workload, but increased the visual attention towards the keyboard. On the other hand, hover visual feedback reduced error rates, but increased the time before the first key press, suggesting that users may become overly reliant on it for anticipating key presses. Combining both feedback mechanisms lowered performance, likely due to user overload. Surprisingly, the physical keyboard resulted in higher error rates and lower usability, likely due to misalignment between the physical and the virtual keyboards caused by tracking errors. This resulted in some spatial uncertainty, lowering the interaction fidelity in this condition. In contrast, the mid-air keyboard resulted in lower error rates, suggesting that users rely more on visual feedback in the absence of conflicting spatial cues, which improved their performance. As expected, visual attention increased in the mid-air keyboard and decreased with the physical keyboard, but no correlation between visual attention and the typing's performance is observed. We present here some recommendations for designers of VR applications requiring keyboard interaction for text entry tasks. First, our study shows that combining two visual feedback mechanisms is not effective. Key press could be used to improve the typing speed, while the hover feedback could be used when typing accuracy is important. Second, the misalignment between virtual and physical keyboards decreases the performance and user experience. Therefore, if physical keyboards are to be used, the current native tracking systems may not be adapted. In this case, the use of external and more accurate tracking systems could be necessary. In scenarios where the use of physical keyboard is impractical, the mid-air virtual keyboards augmented with additional visual cues become an interesting alternative. Finally, reliance on visual feedback may introduce fatigue or distraction. Therefore, a balance needs to be found between visual and haptic feedback mechanisms, user performance, and learning objectives. Our study has some limitations. First, in contrast with previous studies, the text entry in the physical keyboard was based on interaction with the visual keys and not with the physical keys. This may explain in part the decrease in typing speed in our study compared to previous works. Second, we have used only the index fingers for typing on our keyboards. As stated in the introduction, expert typists usually use all 10 fingers to type. Therefore, it will be important to assess performance in the 10 fingers condition. As a future work, we plan to test adaptive systems that can dynamically adjust feedback based on the user's needs. We plan also to run longitudinal studies in order to assess the impact of the different factors on fatigue and on learning to type. Finally, we plan to include these keyboards in simulation-based training scenarios where typing is a key task. This ends my presentation, so thank you for your attention.